Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
It is estimated that by the year 2025, there will be about 175 zettabytes of data on the internet.
Which is just, it's a staggering number.
It really is. And if you are wondering what a zettabyte actually is, well, let's just trace the scale for a second. You have your megabytes, your gigabytes, your terabytes, right?
Right.
And we think of a terabyte hard drive as holding this massive amount of information, but a zettabyte, that is 1 billion trillion bytes.
Wow.
Yeah. If you were to write that out in standard form, it's a 1 followed by 21 zeros.
It really is a scale that completely breaks the human brain,
Yeah.
We just aren't wired to visualize numbers that large. We struggle to truly picture a million of something, let alone a billion trillion.
Exactly. And yet our reality is also defined by the unimaginably small. Like, think about the device you are probably using to listen to this deep dive right now.
The smartphone or computer.
Right. A single transistor inside a modern computer chip can be just 14 nanometers in size.
That's tiny.
It's B000000014 meters. And if you go even smaller, the diameter of a single atom is between 0.1 and 0.5 nanometers. We live in a universe of absolute extremes.
We really do.
And today, we are going to figure out how to navigate it without losing our minds.
Which is why we are trying something a little different for this deep dive. We're going to approach this material as if it were a master class.
Ooh, I like it.
Yeah, so I'm going to be stepping into the role of your lecturer today to guide us through the mechanics of all this.
And I am happily playing the role of the curious student. I'll be asking the questions that you are probably shouting at your audio player. I have my notebook ready.
Perfect.
Our syllabus today comes entirely from section 3.9 of chapter 3 from Contemporary Mathematics. And our shared mission, and we are inviting you, the listener, to join us in this class, is to understand how we can possibly make sense of, compare, and actually calculate these gigantic and microscopic extremes.
It is the perfect mission. Because, well, when you try to do calculations with those standard representations, all those zeros, it is just incredibly awkward.
Oh, yeah.
Like, if you want to figure out how many days it takes to generate 1 zettabyte of data, considering humanity produces about 2.5 quintillion bytes a day.
Just saying that out loud is exhausting.
Right. Trying to punch those literal strings of zeros into a standard calculator is tedious. You are almost guaranteed to miss a zero or add an extra one.
Okay, let's unpack this. The solution section 3.9 gives us is scientific notation. It's a tool to bypass all that tedium. But before we can actually use this tool, we have to know exactly what it looks like.
Right, the format.
Yeah. So, lecturer, what are the strict boundaries of this format? How do I know if a number is actually in scientific notation?
Well, let's break down the anatomy. When we say a number is in scientific notation, we are specifying a very strict standardized form. It has two parts.
Okay.
The first part is the number itself, and the rule here is absolute. The absolute value of that number must be at least 1, but strictly less than 10.
Wait, let me make sure I have that exactly right. At least 1, but strictly less than 10. So it could be 1 or it could be 9.9999.
Yep.
But it can never be 10.
Yeah, exactly. It guarantees that the number to the left of the decimal point is always a single non-zero digit, anywhere from 1 to 9.
Okay, gotcha. To test my understanding as the student here, let's look at what is not scientific notation.
Good idea.
The textbook has some great examples. Check this. If I have 41.7 times 10 to the power of 9, that is invalid.
Correct. Why?
Because 41.7 is way bigger than 10.
Right. You've got 2 digits to the left of the decimal there. It breaks the rule.
And if I have 0.036 times 10 to the power of -3, also invalid.
Exactly.
Because 0.036 is less than 1. So the absolute value of that first number has to sit right in that 1 to under 10 sweet spot.
That is the exact logic. And then the second part of the anatomy is that this starting number is then multiplied by a base of 10.
Okay.
And that 10 is raised to a specific power or exponent. That exponent is what tells us the true scale of the number.
What's fascinating here is just how much cleaner this makes things for fields like chemistry or physics.
Oh, absolutely.
Like, take Avogadro's number. It represents the number of units like atoms or molecules in 1 mole of a substance. In standard form, writing it out requires 24 digits.
Yeah, it's ridiculous.
It's 602 sextillion, 214 quintillion, and so on. It is an absolute mess of zeros.
Reading that out loud or, trying to write it on a chalkboard over and over is just a nightmare.
But in scientific notation, we just look for that single digit between 1 and 9. So we place the decimal right after the 6. It becomes 6.02214076.
Exactly.
Then we multiply it by 10 to the power of 23 because we technically moved the decimal 23 places to get there. It takes up a fraction of the space.
And it immediately communicates the scale. The moment another scientist sees 10 to the 23rd, they instantly know roughly how massive that quantity is.
Without having to count a dozen tiny zeros with their finger.
Exactly. Though as a quick tech check for you listening, the text notes that not all calculators display it this beautifully.
Oh, right, the calculator thing.
Yeah, if you are using something like a standard TI-84 graphing calculator, you might not see the neat little multiplication sign and the superscript exponent.
What does it look like instead?
The calculator might just show a capital E or E followed by the exponent.
Mm-hmm.
So 2.53 times 10 to the 12th power might just look like 2.53E12 on your screen.
That's a really helpful flag. So that E just stands for exponent of 10.
You got it.
Okay, so we know what this packaging looks like. We know the rules of the box. But if I have a normal messy number, how do I practically shrink it down to fit into this strict 1 to under 10 box without completely changing the math?
Well, it all comes down to manipulating the decimal point. Think about what fundamentally happens when you multiply any number by 10.
You just add a 0.
Essentially, yes, you are shifting the decimal one place to the right. 43 times 10 becomes 430. Multiply by 100, which is 10 to the second power, and you move it two places right.
Right, and if we divide?
Then you go the other way. Dividing a number by 10 moves the decimal one place to the left. And this is exactly where negative exponents come into play. A negative exponent is just mathematical shorthand for division by a power of 10.
Oh, interesting.
So multiplying by 10 to the negative 6 is exactly the same as dividing by 1 million. You just sweep the decimal 6 places to the left.
So is it kind of like a seesaw?
A seesaw.
Yeah, like if I alter the number part by moving the decimal to the left, making that front number physically smaller, I have to balance that out by pushing the exponent up.
Nice.
And if I move the decimal to the right, making the front number bigger, I have to push the exponent down.
I love that analogy. Yes, you are perfectly maintaining equilibrium on a seesaw so that the actual underlying value of the number never changes, only its visual representation.
That makes so much sense.
Let's try it out. If you have 145.8141 times 10 to the 8th power, that violates our rules, right?
Right, because the 145 is larger than 10, it needs to be strictly less than 10. So I need to turn that 145 into a 1 point something.
So how do you use the seesaw to fix it?
Let me think. I need to move the decimal 2 places to the left to get 1.458141.
Correct.
Because I just made the front number smaller by 2 decimal places. My seesaw is out of balance. I have to push the other side up.
Exactly, so
I increase the exponent by 2. The 8 becomes a 10. So the final properly formatted notation is 1.458141 times 10 to the 10th.
You've got it perfectly.
Okay, so we have these massive numbers packed into neat little boxes. But reality isn't static. These numbers interact in the real world.
I do.
What happens when 2 of these massive boxed up numbers crash into each other? Let's say I want to add them together. Does this formatting make addition easier or harder?
It actually makes it quite methodical, but you have to follow a very specific golden rule.
Okay, lay it on me.
When you are adding or subtracting numbers in scientific notation, the exponents of the tens absolutely must match.
They have to match. Why?
Think of the powers of 10 as physical units, like fruit.
Fruit, okay.
Yeah, you can easily add 3 apples to 4 apples and get 7 apples, but you can't add 3 apples to 4 oranges.
Right, that doesn't work.
In scientific notation, the exponents are the fruit. If you have 4.5 times 10 to the 4th plus 3.15 times 10 to the 4th, those are both apples.
Because the 10 to the 4th is the same on both.
Exactly. The textbook explains this through the distributive property of real numbers. Because the times 10 to the 4th is identical in both, you can just factor it out. You add the 4.5 and the 3.15 to get 7.65, and the times 10 to the 4th just tags along at the end.
But what if they are apples and oranges?
Good question.
Let's say I'm trying to add 4.5 times 10 to the 5th and 3.9 times 10 to the 3rd. I can't combine them because the exponents are 5 and 3. How do I force them to match so I can add them?
This is where we go right back to your seesaw analogy.
Oh, nice.
The text provides a great strategic tip for this. It is almost always easiest to alter the smaller exponent to match the larger one.
Okay, so in my example, 4.5 times 10 to the 5th plus 3.9 times 10 to the 3rd, the smaller exponent is the 3.
Right.
I need to turn that 3 into a 5 so it matches the other side.
Right. And to increase an exponent by 2 on the seesaw,
I have to make the number part smaller by 2 decimal places.
Exactly.
So I take the 3.9 and I move the decimal 2 spots to the left. It becomes 1039, and now my exponent is a 5. So I have 0.039 times 10 to the 5th.
And now you have apples and apples.
Let me finish the math. Now both my numbers are times 10 to the 5th. I just add the front parts. 4.5 plus 0.039 gives me 4.539.
Yep.
And the exponent just tags along. My final answer is 4.539 times 10 to the 5th.
Gee, very methodical.
Okay, that's actually not too bad. You just have to be disciplined about making sure those exponents, the fruit match, before you try to combine anything.
That's the trick.
But if addition requires this careful balancing act of altering decimals and matching exponents, multiplying these things together must be an absolute nightmare.
You'd think so.
Do I have to match them first for multiplication, too?
Surprise! You actually don't. Multiplication and division are vastly simpler in scientific notation. The exponents do not have to match at all.
Wait, really? How does that work?
It relies on the basic rules of exponents. To multiply two numbers in scientific notation, you simply multiply the front number parts together normally,
Okay.
and then for the tens, you just add the exponents together. That's it.
Wait, so if I have 4.3 times 10 to the 3rd, and I want to multiply it by 1.8 times 10 to the 7th, I don't need to mess with seesaws at the start.
Right.
I just do 4.3 times 1.8, which is 7.74.
Correct.
And then I just add the exponents. 3 plus 7 is 10. So the answer is 7.74 times 10 to the 10th.
That's the entire process.
Wow.
And division works by the exact same logic, just inverted. You divide the front number parts, and instead of adding, you subtract the denominator's exponent from the numerator's exponent.
Okay, that's actually a huge relief. I thought multiplying these massive numbers would break my brain, but it's basically just basic addition for the exponents.
Yeah, it saves so much time.
But here's where it gets really interesting. What if I multiply the front numbers and the result accidentally breaks the 1 to under 10 rule?
Give me an example.
Let's say I multiply 4 times 10 to the 3rd by 5 times 10 to the 4th. The rules say I multiply the numbers. 4 times 5 is 20.
Right.
And I add the exponents. 3 plus 4 is 7. So I get 20 times 10 to the 7th. But 20 is way bigger than 10. It's an invalid format.
That is a fantastic edge case, and you've naturally arrived at the final vital step the textbook lays out.
Phew, okay, I didn't break math.
No, you didn't.
Yeah.
It is incredibly common when multiplying or dividing that your result accidentally falls out of that valid 1 to under 10 range. When that happens, you just apply your seesaw method one last time to tidy it up.
Let me try to fix my own mess then. With 20 times 10 to the 7th, I need the 20 to be a 2.0.
Yes.
So I move the decimal one place to the left. Because I made the number smaller, I push the exponent seesaw up by 1. The 7 becomes an 8. The real finalized answer is 2.0 times 10 to the 8th.
Exactly. You just do the operation freely, and then you tidy up the formatting at the very end to ensure it meets the strict definition.
Wow. Okay, I feel like I actually have a grip on the mechanics now. But let's take this out of the theoretical realm. Doing math on a whiteboard is fine, but how does this tool actually help us understand the real world around us?
Well, if we connect this back to the bigger picture, scientific notation is what allows us to solve practical, mind-boggling curiosities about massive scales without needing a supercomputer.
I like the sound of that.
The textbook exercises have some brilliant applications. Let's look at a question of probability.
Oh, I love probability. What are we looking at?
The text asks us to compare two unlikely events. First, the probability of winning the Mega Millions lottery.
Okay.
The book puts it at 3.304693 times 10 to the negative 9.
Times 10 to the negative 9, so that's a decimal point, 8 zeros, and then the 3. That is bleak.
Very bleak. Now let's look at the probability of being hit by lightning in your lifetime. The approximation here is 2 times 10 to the negative 6.
So decimal point, 5 zeros, and a 2. Also very small, but notably fewer zeros than the lottery odds.
Right. And if we want to know exactly how many times more likely you are to be hit by lightning than to win the lottery, we just divide the two probabilities. The lightning strike is the numerator, the lottery is the denominator.
Okay, let's use the division rules we just learned. We divide the front numbers. 2 divided by roughly 3.3 is about 0.6.
Good approximation.
And then we subtract the exponents. Negative 6 minus negative 9, which is basically negative 6 plus 9, that gives us a positive 3 exponent.
Yep.
So our answer is 0.6 times 10 to the 3rd.
And 10 to the 3rd is 1,000. So 0.6 times 1,000 is 600.
Oh, wow.
The math clearly shows you are roughly 600 times more likely to get struck by lightning in your lifetime than to win the Mega Millions.
Note to self. Stop buying lottery tickets during thunderstorms. That's just terrible odds.
Definitely.
What else? What other real-world scales can we tackle?
Let's look at human biology and scale it up to the planet we live on.
Mm-hmm.
This one is genuinely staggering.
I'm ready.
According to the text, if you extract a single strand of human DNA and stretch it out, it is about 2.066 times 10 to the second centimeters long.
10 to the second is 100, so about 206 centimeters. That's roughly 2 meters.
Right.
That's incredibly long for something coiled up inside a microscopic cell nucleus.
It is. Now, consider that there are approximately 3 times 10 to the 13th cells in the average human body.
3 times 10 to the 13th. That is 30 trillion cells.
So the question asks, if you were to take all the DNA in every single cell of just one human body, stretch it out, and lay it all end to end, how far would it reach?
Okay, we can do this. We just multiply the length of one strand by the total number of cells.
This here.
I multiply the front numbers. 2.066 times 3 is 6.198. Then I add the exponents. 10 to the second times 10 to the 13th. 2 plus 13 is 15.
Exactly.
So the total length of DNA in my body is 6.198 times 10 to the 15th centimeters.
Spot on. Now for the really wild part. The book asks us to compare that total length to the Earth's equator. The circumference of the Earth at the equator is 4.007 times 10 to the 4th kilometers. If you wrap your DNA around the Earth, how many times would it encircle the globe?
Wait, hold on. We have an apples and oranges problem here again.
Do we?
Yeah, my DNA length is in centimeters, but the Earth's equator is in kilometers. I can't just divide those, right?
You spotted the trap. You absolutely cannot. You have to convert them to the same unit first.
Huh. Nice try.
The easiest way is to convert the DNA length from centimeters into kilometers.
Okay, how do I do that using our rules?
Well, there are 100,000 centimeters in a single kilometer. 100,000 is a 1 with 5 zeros, so that is 10 to the 5th power.
Gotcha.
To convert centimeters to kilometers, you just divide your DNA number by 10 to the 5th.
So my DNA length is 6.198 times 10 to the 15th. I divide that by 10 to the 5th. The front number stays 6.198.
Right.
For the exponents, division means subtraction. 15 minus 5 is 10. So my DNA length in kilometers is 6.198 times 10 to the 10th. That was surprisingly painless.
It really is. Now we can finally do the big comparison. Divide your DNA length in kilometers by the Earth's equator in kilometers.
Okay, DNA is the numerator. 6.198 times 10 to the 10th. Equator is denominator. 4.007 times 10 to the 4th. I divide the front numbers. 6.198 divided by 4.007. That's roughly 1.5. Now I subtract the exponents. 10 minus 4 is 6. So my final answer is roughly 1.5 times 10 to the 6th.
And 10 to the 6th is 1 million.
1.5 million times. The DNA in my single human body could wrap around the Earth 1.5 million times.
It sounds like pure science fiction, doesn't it?
It really does. And honestly, doing that math just now was incredibly easy. I literally just divided 6 by 4 and subtracted some tiny numbers.
This is exactly the point.
If I had to write out 30 trillion, multiply it by 206, and then somehow convert all those massive trailing zeros, I'd never even attempt it. I'd get lost on the page.
And that, right there, is the true power of scientific notation. It takes the impossible, overwhelming scale of the universe and elegantly scales it down so that it fits neatly onto a single piece of notebook paper.
So, stepping out of my student role for a second to summarize what we've covered today, it really feels like scientific notation isn't just a formatting rule that math teachers arbitrarily force you to learn.
Definitely not.
It is truly the ultimate lens for human comprehension. It lets us zoom out to the edges of the galaxy and zoom in down to a single virus without ever losing our place or drowning in zeros. It's a cognitive tool that gives us a handle on the infinite.
That is a beautiful way to phrase it.
Yeah.
And it actually brings us to a profound consideration that the textbook poses right at the end of section 3.9.
Oh, what does it leave us with?
The text lists a few of the most extreme numbers we currently know. It notes that the smallest theoretical measurable distance in physics, the Planck length, is roughly 1 times 10 to the negative 35 meters.
Negative 35, just impossibly tiny.
Then it looks outward. The distance across the entire known universe is estimated at 4.4 times 10 to the 26th meters.
Okay.
And the total number of particles in that entire known universe, roughly 4 times 10 to the 80th.
4 times 10 to the 80th. A 4 with 80 zeros after it. That accounts for all the particles in existence.
This raises a deeply philosophical question, one to leave you with as you ponder these extremes.
I'm listening.
Do these numbers, these massive positive and negative exponents, represent the actual or physical hard boundaries of reality itself? Is there simply nothing smaller than 10 to the negative 35 and nothing more numerous than 10 to the 80th? Or are they simply the current limits of what the human brain and our current technology are capable of measuring?
Wow. That a phenomenal thought to end on, because just a few decades ago, the idea of 175 zettabytes of internet data would have seemed mathematically absurd.
Exactly.
Who knows what scales we will be measuring tomorrow, whether we're looking at the jagged white line of a broken arm on an X-ray or trying to measure the diameter of an atom. We are constantly just trying to bring clarity to the murky waters of reality. And thanks to scientific notation, we at least have the right lens to try.